So our webinar is officially live. Welcome everyone.
All right. Well, welcome everyone, and thank you, Kayla Villon, who is a member of Water UCI staff, for setting this up. My name is Dave Feldman. I'm the director of Water UCI. It's a real pleasure to invite you to our first Water UCI colloquium of the 2024-25 academic year. And it's a great pleasure to welcome James Earthman, who is a professor of material science and engineering and biomedical engineering here at UCI. This is a very unusual talk for us in that it really is focused very much on the science of water quality. Jim is going to talk about anti-fouling nanobubbles for water purification and desalination. Many of us should be aware of the fact that water purification is a very important issue in all societies. And certainly here in Southern California, desalination is growing in regional importance. So we're really looking forward to this presentation. Jim will speak for about 40 minutes and we'll then have time for questions. You can insert your questions in the Q&A box, and as time permits, I'll call on you. With that, Jim, it's all yours.
Thank you very much, David, and thank you so much for giving me this opportunity to talk to your group. This is a great topic for me to go out and talk to other groups because it's not mainstream material science, as you can see. It's really more to do with water and gases than solids, although our application has to do a lot with solids, and that's how I got interested in this. I'm particularly pleased to have Bill Cooper on this webinar because Bill, while he was director of the Urban Water Research Institute here, was actually instrumental in me getting involved in this, although he probably didn't know that before recently. But Bill, thank you for being here, and I hope you have weathered the storms down there in Florida well. I haven't heard anything about your situation, but I hope it wasn't too bad. All right, so with that, what I like to do when I start a talk on nanobubbles is show a couple of pictures. This is a couple of beakers that have water in them. One of them has nanobubbles in the water and one does not. And I always like to ask, get a raise of hands for which one you think it is. Is it T or is it C? And I won't do that with the Zoom, but it is T that has the nanobubbles, even though C has some macroscopic bubbles, and you can actually see it is in the water. C is for control. That means there's no nanobubbles there. T is for test. And if I shine a laser pointer through those two beakers at the same time, you'll see in the beaker with nanobubbles, and this is after 2 days of creating the nanobubbles, you can see a trace, a clearly defined trace through the beaker. It's actually on the other side of where the laser pointer is. I'm shining it from your right side and through both beakers, and you can see the trace pretty clearly in the beaker labeled T and not so clearly with the other beakers. So you can see that the nanobubbles are scattering light if it's collimated and from a laser. But in diffuse light, very difficult to see them. You can't really see those bubbles that are so small. And so after 16 days, you can do the same thing. And lo and behold, you can still see that trace. So the nanobubbles, one characteristic about nanobubbles, very interesting, very useful, I think, is that they persist for a long time. Some people have even claimed months, and I've seen evidence of that too with some of the nanobubbles we create. They are very, very stable in water, and they're not that buoyant. Their motion is primarily determined by charges in the water, and we'll get into that a little later. So you might be wondering, well, how is a guy in material science and engineering involved in research on something like this? Well, this is how it started. We were conducting research at Three Mile Island Nuclear Power Station at the time. This was many years ago. This is before they shut the whole thing down, and actually, it's now being resurrected to go back into operation. There was actually two nuclear reactors on the site. One was closed down after the accident. One continued running for many years and was actually one of the most successful problem-free reactors in the country. And they were very progressive, and they were willing to work with us on bacteria that we were working on that could actually protect the pipes in a system like this from corrosion. The problem that they had, though, was very difficult, and as far as I know, they still haven't overcome it. I'm going to be trying to talk to them about what we're doing in the not too distant future, but they had this problem with their secondary cooling water system. That system basically took in river water. 3 Mile Island is actually on a river, and they bring in water from the river and they use it in their secondary cooling water system, which cools the primary system, which has pristine treated water, very clean water that goes into the nuclear part of the plant. But that system has to be cooled by the secondary system, and it just has coarse filtered river water. And these tubercles can form on the pipes in that secondary system. And once they form, they are very tenacious. This is actually after they tried to remove the tubercles by during a routine shutdown of the plant. They took spheres with sandpaper on them. They flushed them through the system to knock the tubercles off. But that, as you can see, it didn't really do much in terms of removing them. And this is the problem that they create eventually, is that these tubercles get colonized by bacteria that can induce corrosion. The upper parts of the tubercle are typically colonized by aerobic bacteria. They consume the oxygen coming in, diffusing into the tubercle. And then at the bottom, there's typically anaerobic bacteria like sulfate-reducing bacteria that can thrive down there because there's very little oxygen as a result. And the sulfate-reducing bacteria create iron sulfide. And the iron for the iron sulfide comes from the pipe wall. And so as you can see, you tend to get this localized corrosion, and eventually the bacteria will eat through the pipe wall, and then you have a leak and you have to shut down the system. Very expensive. Here's another pipe that had this problem. The localized corrosion was actually going down a weld seam for the pipe, the one weld seam that the pipe had. Bacteria are very efficient. They always colonize where they can get the fastest corrosion going, the most iron sulfide producing, and at the weld seam it's weaker there, and so that was a susceptible region for localized corrosion, and they were just going down that weld seam. And so what the operators decided to do was to weld a bead on the outside of the pipe just to extend the life of that pipe a little longer. But eventually, as you can see, they had to remove it. So this was a big problem there, and there really wasn't any way to solve the problem while we were working with them on this. Now, about that time, I happened to be in the Office of Research. I was Associate Vice Chancellor there, and I went to the Canadian Consulate in Los Angeles, and I met a couple of guys from a company in Irvine, and they had a water treatment system that they were talking to people in Canada about, and so they were there, and so since they were from Irvine, I of course wanted to find out what they were doing, and they mentioned that they have their water treatment system in 36 different golf courses in Southern California, and they could demonstrate that if you use their system in the irrigation, you can grow greener grass with less water, and they could demonstrate that, and they could convince greenskeepers, who are typically very conservative people, that this is something they should lease, and so they were doing that. And I thought, well, I need to introduce these guys to Bill Cooper, because he's the director of our water center. He should know about this. So I set up a lunch with me and Bill and these guys, and they presented what they were doing, and it was had to do with a magnetic water treatment. And I didn't know at the time, I guess there were a lot of people claiming that magnetic water treatments were beneficial for some reason or another, but these guys didn't seem to know why it was working the way it was. And Bill didn't seem too interested in it at the time. But there was one photograph, and it's this one down in the right-hand corner that I saw while they were talking, that really intrigued me. They said that whenever they install one of their systems on the irrigation lines, they have to remove the sprinkler heads for a while to flush out this debris that comes out. And after a couple of days, all the debris comes out, and it's fine. You don't have to take the sprinkler heads off anymore. So anyway, I looked at this debris, and I thought, well, the only place for that debris to come from is from the pipe walls. It must have been fouling the pipe walls before it came out. And somehow the system was able to get that to come out. All right. And I thought about 3 Mile Island. So I asked the engineer at 3 Mile Island if he could send a pipe sample and some water. And I asked the company that these guys were with in Irvine if they wouldn't mind helping me build a proof of concept experiment to test this with pipes from 3 Mile Island. So, Bill, if it weren't for you, I wouldn't have ever gotten into this area at all. So, thank you for doing that, and I appreciate you coming to lunch with us, even though you didn't follow up with them, and I understand why you didn't. So we set up this proof of concept, and the pipe that was sent was in service for 30 years. It had a lot of tubercle deposit on it. They sent it wet, and they also sent two carboys, I think, of water from the secondary water system. So we used their water. We set up two different test systems, two flow loop systems, one without their treatment, one with their treatment. We cut the pipe into two sections. We put one piece in each of the flow loops and started running the flow loops, one with the treated water, one without treated water, to see what would happen. And so after 48 hours, we looked at the two systems, and this is an aquarium that we used as an expansion tank for one of the flow loops that had their system. This is their AMF. I call it AMF. It's alternating magnetic field, and I'll explain why later. And you can see that the water was fairly clear here. It was not, didn't look too bad. Here's the water in the control system, and this is how it came. This is exactly how the water looked when it came from 3 Mile Island. It was rusty colored. So we took some of the water out, and sure enough, it looked like you could almost drink the treated water. This is only after 48 hours of this AMF treatment. We looked at the pipe samples, again after 48 hours. Well, the control pipe looked exactly the same, still had the same amount of deposit on it that it had when we put it in. The treated pipe looked a lot different, though. It had a different color on the inside. And if you go back to, let's go back and I'll show you. If you remember, there was a change in color as you get down to where the sulfate-reducing bacteria producing iron sulfide, the color changes to a gray color. Here's another example. Well, this is the gray color I was seeing on the inside of that pipe. So we were down, I knew we were down close to the substrate of the metal at this point. There was only this one little nodule that was left from the tubercle that sat on that pipe. So this is pretty dramatic. I thought, wow, I don't know what this is doing, but this is really interesting. And in the expansion tank, in the treated water, there was this pile of debris that had formed, apparently from the pipe wall that had just fallen off. I thought, wow, this is something that's really, really dramatic, and I need to find out what's going on here. So I started to talk to people on campus about it because it was clear that the people at this company didn't really understand what they were doing to the water. They said they were creating more energy in the water, but that was about it. That's about their best explanation for what was going on. So I eventually got Ruqian Wu in physics involved, Professor Ruqian Wu, and we started talking about this. And he suggested, I think they may be creating nanobubbles. Now, I didn't know what a nanobubble was at that point. And so I started looking into it. And the one thing I did know about this system is that the water that flows through it does undergo an alternating magnetic field. It's got permanent magnets that are arranged in such a way so that when flowing water comes through there, the water molecules experience a magnetic field that's oscillating, right? Depending on the flow rate, that'll determine your oscillation frequency. So the flow rate's very important, and that's all this was doing. No chemicals were added, and you don't have to supply any power to this. The flow of the water itself provides the kinetic energy for this, right? Anything that's going on here is driven by the kinetic energy of the water. There's no other power input. So that's pretty good because that's energy passive, right? If you got flowing water already, you don't have to add any more energy to this really. So I started to look into the literature for how this thing might be creating nanobubbles. And I actually found some papers that did suggest, even some that suggested that nanobubbles could be created by a pulsed magnetic field or an alternating electric field. The electric field was also a way you could generate bubbles, apparently, in water. And the explanations were that if you expose water to these fields that are oscillating, you can affect the hydrogen bonds in a way that will destabilize dissolved gases in the water so that they'll precipitate out as bubbles. Okay? And that, I didn't know a lot about water chemistry then. I still don't know about water chemistry. At the time, I thought water was pretty well understood, liquid. We do get exposure to liquids in material science when we talk about molten metals and things like that. We solidify materials from molten liquids, but I didn't have any real experience with water. But this seemed like, this was possible. And I thought, well, this might be how this is working, if it's creating nanobubbles, whatever those are. So then I started looking into what nanobubbles are, and I was kind of horrified. But I did find that if we take deionized water and we run it through this AMF system, I can get this effect with the laser pointer. This is called the Tyndall effect, and this is what I showed you in the beginning. So, and people were reporting that this is what nanobubble containing water does. The problem, though, and the horrific part of it, is there was no real good theory for why nanobubbles should exist. There was a lot of skepticism out there in the literature. It was pretty evident. A lot of people didn't believe they could exist. And there's a good reason for that. The other thing I wanted to mention, though, is in addition to doing this Tyndall effect test, we also measured the zeta potential of deionized water that we ran through this thing. And it was about minus 36 millivolts. And we did 3 replicates, and we were pretty convinced that's what the zeta potential is for this. And of course, if you don't treat the water, we don't get anything for deionized water for this zeta potential measurement. This was done with an Anton Parb instrument. And so I looked up in the literature. Yeah, that's what the nanobubble should have in terms of a zeta potential. So that was also evidence that this thing was creating nanobubbles. But I couldn't find a good theory for why nanobubbles should exist. There's other conventional nanobubble generation methods that were already out there. People were using. This is one that we have in my lab now. It's what I call dissolved gas decompression. You put water in a container. This is actually a modified seltzer bottle. You put gas pressure on top of that water. 100 psi is enough. And then you release the water out a small orifice and tube, and microbubbles are produced. The water comes out cloudy, and after the microbubbles shrink, they actually shrink at below a certain size, then the water gets clear, and that's when you have nanobubbles. Okay. Here's another method for making them. This is called a Nikuni pump. It's made by a company called Nikuni in Japan. They have an American division now that are creating these pumps specifically for generating nanobubbles. And they can show you that you can put different gases in the nanobubbles and create nanobubbles with different gases in them. And so if you take nanobubbles from those types of techniques, this is from the seltzer bottle, this dissolved gas decompression, you do get the zeta potential in this range of minus 30 to minus 40 millivolts, which you'd expect for nanobubbles in deionized water. So the problem is this. Macroscopic bubbles, as we know, are just buoyant. They go up to the surface and they dissipate at the surface typically. A microbubble below 50 micrometers in diameter shrinks. Okay, the reason why it shrinks is that that size or smaller, the surface tension pressure is high enough to push the gas back out into solution. So the bubble shrinks, the gas goes away. And so most people who observe this, and we're going to look at it in a minute, thought that these microbubbles just shrink to annihilation because the surface tension pressure is only going to increase as the bubble gets smaller. So here's some microbubbles here. This is a video of microbubbles shrinking. You can see that it looks like they just go away. They go away to nothing, right? Here's another replay of that. Okay, microbubbles, and they're shrinking, right? This is observable in the optical microscope, no problem. The explanation for this is provided by the Young-Laplace equation, where you can see for equilibrium pressure of a bubble, you've got internal pressure, you've got external pressure, and then you have this surface tension pressure here, okay? And again, when the bubble is less than 50 micrometers in diameter, that surface tension pressure is high enough to start pushing the gas providing this out. And the surface tension pressure, you can see this is the surface tension here, gamma, divided by the diameter of the bubble. So it goes up by 1 over the diameter of the bubble. And it's negative because it's compressing the bubble, making it smaller. Okay? This was the conventional theory at the time I started working on this. There was no way to explain why nanobubbles should exist. So I fortunately at that time had a graduate student from India, Patrick Sapudi, who had a really good background in chemistry and physics. And I started talking to him about this, and he got excited and interested in it, and he wanted to work on it. And I said, okay, let's work on a theory for this. All right. And so we did. Some reason my slide's not advancing. Let me try this way. Okay, there it goes. All right. So again, nanobubbles were observed by several research groups. There were a lot of groups in Japan for some reason. I'm not sure why so many groups are working on this in Japan, but a lot of groups in Japan were working on what they were calling nanobubbles. And they were reporting that nanobubbles tend to be around 20 nanometers to 1 micrometer in diameter. And they can be stable for many days. They were already seeing this stability, long-term stability. And the nanobubbles were typically negatively charged, as I showed you with the zeta potential. And a lot of people were attributing to this to OH ions, which are negatively charged. In deionized water, that's about all you've got in the water that's negatively charged. So that kind of made sense to me. And also that's interesting about the nanobubbles is they repel each other, so they don't coalesce. They don't, come together and make bigger bubbles because they're repelling each other because they're all negatively charged. And a lot of people were reporting this minus 30, minus 40 millivolt zeta potential for them. And as a matter of fact, Takahashi, as you can see here, did a study where he measured the zeta potential for smaller and smaller microbubbles, and you can see that the zeta potential doesn't really change in neutral water. It stays within that, minus 30, minus 40 millivolt range. So that's kind of interesting. That was kind of interesting. Zeta potential doesn't change. Whatever's on the surface of the bubble doesn't seem to be going away as it gets smaller. All right, so we started looking at how OH ions could be doing this. And turns out, not long before this, there were some publications which showed that OH ions actually have a huge affinity to gas-water interfaces. They will knock other ions like chlorine ions off the surface, off the gas-water interface to get there. And this was being reported. Bayan Hersfeld, as you can see there in the third bullet, attributed this strong affinity to suppression of dipole moment fluctuations by the ions and a reduction of the loss of hydrogen bonds compared to water molecules at the interface. So there was a lot of literature and evidence to support the idea that OH ions have a much lower energy at a gas-water interface, and they want to stay there. So we introduced another term to the Young-Laplace equation. And this is a pressure due to the repulsion between ions on the surface of the bubble. We started doing calculations of what you would expect in terms of concentration of OH ions on a nanoscale bubble. And it turns out that you really don't get enough ions to do anything. They're not close enough together on the nanobubble to repel each other. Therefore, you don't get stability. But ironically and counterintuitively, if you take a microbubble and calculate how many ions it has on its surface and then shrink it by about 100 to 1,000 times, you'll find out that the ions that you start out with start to get really close together, and they start to repel each other. And so that was our theory. That became our theory, that it was the microbubble shrinkage itself, the thing that made it counterintuitive that nanobubbles could be stable, that actually leads to the stabilization of the nanobubble. And one thing that was nice for me as a material scientist is that the ions, as they get closer together, should naturally form a closed packed array. Now, we have lots of closed packed arrays in material science and crystal structures. And I knew how to treat a closed packed array of atoms, or in this case, ions, that had forces between them. And the force, of course, here results from the Coulomb charge that each ion has. And we could calculate what this repulsion pressure is. And if you work through the math, you will find that the repulsion pressure, I'll just skip to this last result because this is really the important result. I can go through these other equations if you like, but I just want to show you this result here at the bottom. That repulsion pressure goes up by 1 over the diameter of the bubble to the 4th power. Okay? So that means it's going to catch up with the surface tension pressure, because the surface tension pressure goes up by 1 over the diameter. So that was great. So we did some calculations, and lo and behold, you do get that this repulsion pressure will balance the surface tension pressure in the range of bubble sizes that were being observed for nanobubbles. The largest of which should be about 1,100 nanometers, because that corresponds to starting out with a 50 micrometer microbubble. If the microbubble is larger than this, it won't shrink. Surface tension pressure is not high enough. But if it's this size or smaller, it will shrink to the nanoscale. And according to our theory, it should stop shrinking because of the repulsion pressure at about 1,100 nanometers. Okay? So first thing I wanted to do when we saw this is see if there was any experimental data to confirm this, and it turns out there is. This is some data from a group in Japan who did zeta sizer nano measurements. This is a light scattering technique. They could measure the zeta potential. They could also measure the size of the nanobubbles with this instrument. And it's a light scattering method. It uses a CCD camera. And they measured the distribution of nanobubbles produced by a large diverse microbubble distribution. So they would start out making microbubbles. They wait for the microbubbles to shrink, and then they would make these measurements of the nanobubbles. Okay, and these are the average of 10 replicates for them. The mean microbubble diameter they start with was 56 micrometers, so even above the 50 micrometers in size, but anything larger than 50 micrometers won't shrink, so it won't form a nanobubble, according to our theory. And if you look at the maximum size here, this is just after production, it maxed out right about 1,000 nanometers. A little bit later, 24 hours later, you can see, it's right around 1,100, where you would expect from our theory. So that was pretty good confirmation. I thought that was pretty excited with that. Then we found another paper. This is by another group in Japan, different group. They created nanobubbles the same way with a large distribution of microbubbles. But in this case, instead of measuring using a light scattering technique, they use freeze fracture replicas. And freeze fracture replicas are really difficult to make. You have to have a very expensive machine to make them. But basically, what is done is you freeze a water droplet with, in this case, nanobubbles in it instantly inside this machine. And while the droplet is frozen, a wedge comes in, fractures the droplet, and then replica films are made on the fracture surfaces of that droplet. And then the replicas are taken out, put in the transmission electron microscope, and whatever was inside that droplet is then observed in the transmission electron microscope. And so they measured these nanobubble sizes, these black circles, and the agreement was so good with the other data that I just showed you that they actually plotted that data as well. So this is actually the data from this Ushikobo study that they plotted along with it, because they said, oh, look, we got very good consistent results with theirs. And again, the maximum was right around what we predicted with our theory. So I was really happy with this. I thought we must be onto something here. And the other thing about our theory is there's no fudge factors. It's all based on first principles physics. The number of ions that you calculate, that you start out initially on the microbubble, you can get fairly accurately with the pH of the water and the Debye length. And so it's a pretty straightforward calculation. So I was really happy with this because we had, I thought, a really good theory for why these things exist and why they're so stable and why they last so long. Because if you look at our prediction, the pressures balance, these two pressures balance at really high pressures. This is in the megapascal range here. So, it takes a lot of it would take a lot of pressure, external pressure, to destabilize these things, right? So, and that was actually one of the criticisms of our paper. And when I explained to them, look, yeah, you can put a lot of pressure on these things, nothing will happen, but look at where they're balancing at. After I rebutted that comment, we got accepted. Anyway, what I was really interested in was not so much the nanobubbles themselves, but how they interact with nanoparticles. And this is what I was interested in. Nanoparticles have a very high surface tension as well. And if they encounter a nanobubble, they will bind to it. The hydrophobic forces can actually overcome differences in charge between the nanobubble and the nanoparticle. In other words, if I have a particle that's minus 5 millivolts, it'll still bond or bind to our nanobubbles, which are minus 30 millivolts or more. So this hydrophobic force at this scale, size scale, is really powerful. Now, these particles may not be stable. They may be embryos. They could be at the solubility limit of this solid, and they could just be forming and dissolving over time. But if they bind to a nanobubble, their surface tension is going to go down, and they're going to become stable. And if we keep doing that, we can force the concentration of that solid to below the solubility limit. Here's some freeze fracture replica images of some nanobubbles and nanoparticles that were published by Uchida and his group. And you can see here, this is for 1% sodium chloride. So these are sodium chloride nanoparticles here. And you can see that some of them are binding to this or seem to be binding to this nanobubble. This is without the nanobubbles. This is just with the nanoparticles. This is with the sodium chloride without the nanobubbles. So here you can see the nanobubbles, pretty clear distinction. And you can see the nanoparticles are binding to them. They also did the same thing with wastewater. And of course, with wastewater, you're going to have lots of nanoparticles. And you can see around this nanobubble, there are a lot of nanoparticles bound to that nanobubble. Which makes sense because these nanoparticles would be very hydrophobic. So we wanted to test this in a basic research study, and we used an instrument called a nanosite. It's another scattered light system that you can measure nanoparticles and nanobubbles together. The nice thing about this nanosite is it also gives you the relative intensity of the scattering center that's producing the light. So it can not only measure its size, but it also can measure its the intensity of the light coming from it. If we take deionized water and just put calcium carbonate in it, we would get one peak in the object size. This is at the solubility limit of the calcium carbonate, very low, 0.005 molar. And we get one peak in relative intensity. We get one peak in object size, what you'd expect with just calcium carbonate. When we put the nanobubbles in, same water, we get three peaks. We get a high peak, which is apparently the nanoparticles because they have higher index of refraction. They should scatter light more. The nanobubbles are probably this peak here, the low peak. And then we have this big peak in the middle that goes out to larger sizes. We believe those are the clusters. Those are clusters of nanobubbles and nanoparticles together. And they go out to much larger sizes. It's hard to see on this image, but they do go out to larger sizes. So here's the theory for the interaction of nanobubbles and nanoparticles. You've got something at the solubility limit. That's typically where you're going to be at in one of these surface water systems, because if there's more calcium carbonate in the water, it's going to deposit somewhere, and the concentration will go back down to the solubility limit. If there's not enough calcium carbonate in the water, then something will dissolve. The calcium carbonate will dissolve somewhere and bring the concentration back up. So you're typically around the solubility limit of that compound in the water when you have it depositing on the pipes, when it's fouling. If you add nanobubbles, you're going to form clusters. Those clusters are going to stabilize these embryos over here, and they're going to keep them from dissolving back in solution. And you're going to force the concentration below the solubility limit. If you keep adding more and more nanobubbles to this, the concentration won't be able to catch up. You can keep it down, and you can keep dissolving the fouling solid that you got in the system by just adding more and more nanobubbles this way. All right, we did some experiments to check this. Here we took some solid calcium carbonate. We added DI water. We put DI water in this. We put nanobubbles in some of our experiments. We had untreated controls, and after 20 hours, you can see the mass loss of the calcium carbonate was 0.59 here. For the untreated control, it was 0.35. This is nanobubbles created from the gas pressure rate, a little bit higher, but not that much compared to the EMF system. After 72 hours, we had a mass loss of 1.57 grams. And in the DI untreated water, we had 0.04, not much change here. Now we expected some loss because we start out with DI water. There's no calcium carbonate to begin with, so you're going to dissolve some calcium carbonate just to bring the concentration up to solubility limit in the control. So that we expected, but it wasn't nearly as high as the mass loss we saw with the nanobubbles, especially with AMF. So this is our strategy. We form these clusters. We can force the effective concentration of the solute down below the solubility limit and start dissolving it as much as we want, as long as we can keep adding more and more nanobubbles. We checked this, see if this would work with cadaver arteries that had plaque. In this case, instead of calcium carbonate, we had calcium phosphate in the plaque. And we measured the size of the plaque using IV-OCT in Zhongping Chen's lab here in biomedical engineering, and before and after adding nanobubbles to the artery. So here we took our ex vivo, these are for cadavers, artery sample. We ran a ringer solution, which is a intravenous fluid through the artery, so it had the same approximate concentration as blood and of salt and other additives, and also nanobubbles in some cases. And so we wanted to see if the nanobubbles could actually lead to greater dissolution of the plaque. And in fact, we did find that. This is after 2, 4, and 6 hours for one of the arteries that we were testing. And you can see quite a bit of change here in terms of the change in volume, reduction in volume of that plaque. This was in a control artery, very similar. Again, we were using rigorous solution without phosphate in it, so we did expect a little bit of reduction in the plaque in that solution, but it wasn't nearly as much as with the nanobubbles. And here we did it again. This is for 3 hours. This is after, 4 hours with nanobubbles for 5 different samples. This is 5 control samples. And again, big difference in reduction of that plaque. We've also been recently talking to some people who set up a test system in Rialto. They're hopefully going to be working with me and Diego Rosso in the future with DOE funding. This was just a pilot project that they were able to do with some money from, I think, the CEC. And they were able to set up 2 systems over here for treating wastewater with RO, with reverse osmosis. They have 2 AMS systems. One is a dummy system. One just has a empty core, no magnets in it. The other one has magnets, and here are your RO membranes over here. And they were able to actually increase the life of the membranes without maintenance by a factor of 5 with the active nanobubble generating AMS system. So that was very promising. So we're now working with them on a proposal to DOE to continue working on this for reverse osmosis. And this is where I think we can have a big impact on water purification and desalination, is because, like pipes, RO membranes and other fine filters also get fouled and get clogged up and have to be cleaned or replaced after a certain period of time. The more frequent that is, the more expensive it is, of course, to run the plant. And so, in conclusion, I just want to say nanobubbles naturally becomes very stable under ionic repulsion pressure that balances surface tension pressure. That's our theory. It constitutes a hybrid object made of gas containing a 2D ionic solid. It's really kind of like a solid around the liquid, that ionic shell. And the nanobubbles can be produced easily and plentifully by multiple methods, including this alternating magnetic field generation method that doesn't require any external power, just flowing water. And experiments have shown that treating water and other aqueous solutions with nanobubbles leads to formation of stable clusters with embryonic nanoparticles that can drive dissolution of undesirable fouling deposits. And so with that, I will conclude and take any questions. Thank you very much for your attention.
Jim, thank you. That was great. Really good job. The theory, the experimental work, and the application, really nicely done, and really appreciate it. We've got some time for questions. Please put your questions in the Q&A box, and we'll take them one at a time. I had a quick question, Jim. Where do you see, you mentioned at the end some of the applications with respect to reverse osmosis membranes for desalination, I assume also for wastewater recycling. Are there any specific places other than Rialto in California and the work you're doing where some of this nanobubble work is being applied to those issues? Anywhere that you're aware worldwide?
I know people are working with systems that generate nanobubbles, particularly in Japan, as I mentioned, and they've tried to do all kinds of things in addition to what we've been trying to do with RO. And I think in general the results have been pretty good, but there just hasn't been a concerted, coordinated effort, I think, to combine all of the data being generated out there. A lot of it's proprietary, of course. Not all of it's being published. But I know that there are other people working on this and starting to get good results. I think with our theory and the way we measure nanobubble concentrations, we probably have a good chance of being better at optimizing some of these approaches. And that's where I'd like to really make a contribution is, okay, you're creating nanobubbles, but how do you know you have the best concentration of nanobubbles? Or how do you know you can't create a higher concentration? Or do you need a higher concentration? Or is that detrimental for some reason? So there's a lot of questions that still need to be answered. So far, people have just been throwing nanobubble generators at things and seeing what happens. And, that's not real science. It's not even really good engineering. And so
Right.
I think there's a lot of room now for really perfecting the methods so that we can optimize what we're doing with these things.
Excellent. Well, we got a question from your colleague and mine, Bill Cooper, and I'll go ahead and read it for you. Have you thought
Okay.
about removing O2 and putting another gas, N2O, for example, or maybe argon?
Yeah, we have thought about that. Others have thought about. You can find publications on that. There's a lot of interesting things that could be done with different gases. Uh, we actually have been looking at putting iodine vapor in with mixing it with air in nanobubbles. Turns out that seems to be a very good antimicrobial, probably because bacteria have adapted to exploit air-containing nanobubbles, and when they get one that contains iodine vapor, they start to try to get the air, and it kills them. So that's been something we started to study with a system which I have in my lab now that can put iodine vapor in. But there are other gases, and one thing we did with the AMF I didn't mention was we were able to take dissolved helium and dissolved nitrogen and dissolved oxygen in water, where we controlled the gases that the water was being exposed to. Instead of just aerated water, we took out the air and we put in nitrogen, helium, and oxygen. And we found out with AMF, the highest concentration of nanobubbles were with the nitrogen. So it appears that the nitrogen in air is what is primarily being used to generate the nanobubbles with AMF. That's the gas that's coming out and precipitating
Right.
to form the nanobubbles with that system. So that system is pretty much limited to whatever you have dissolved in the water. But with the other systems, the Nakuni pump and that little container system, uh, you could put just about any gas in there and produce nanobubbles with that gas. So there's a lot of opportunity, I think, a lot of applications that could be done with different gases. You're right, Bill.
Mhm. Very
I
good.
only have so many
We have
hours in
time
a
for
day,
other
so I can't do
questions.
everything. I'd like to explore all these things, but you can only do so much.
Yeah, it's a good start. While we're waiting for some other questions, I had another one that I'd been pondering during your presentation. You mentioned the funding from the Department of Energy. I assume there's also, or should be, interest from EPA, perhaps water agencies here in California or elsewhere. Where do you think the future of research funding in this domain will come from? And what will it take to spark greater interest?
It's a good question, and one thing I have noticed about the more local agencies is they tend to be much more conservative, a little more stodgy uh, in terms of wanting to continue using the conventional methods. Um, Although this test bed in Rialto was funded by the state, uh, and I can't remember which. I think it was a Water Resource Board or something like that that funded it. I wasn't actually
Mhm.
involved in that because it wasn't enough money for me to be involved in. But um, they were able to set up this skid to test the AMS systems there, and so that was fairly progressive. Um, but they had a lot of help from the city of Rialto. The mayor of Rialto in particular was very positive on doing this. So, local governments, I, I I don't know how far you're going to be able to get with them. They don't have as much money, of course, and they tend not to be so far thinking, I would say, in terms of new techniques like this. I think it's going to have to come from the federal government, but again, they have to be convinced that there's a real scientific rationale for this and a good theory for explaining this. That's why I wanted to have a good theory for why these things exist, because there really wasn't one.
Yeah, and one of the comments that was added, I think by Bill, in the chat is that Orange County Water District, which is of course our wholesale provider here in Orange County, has a lot of RO membranes and they might be a good local partner. It's a great suggestion. They're certainly heavily invested in recycled wastewater through the groundwater replenishment system.
Yeah.
So just something
Yeah.
to think about.
Yeah, it is. And Diego Rosso has been working with them some, and I know Diego's very much uh, for this research. He's been working with me. He actually has one of his PhD students in my lab doing some work. So we're already starting to get the pieces, and he would probably be working with this group that had the skid in Rialto. He's probably going to be with us on that if we get funded from DOE. So Diego knows he has the connections with the Orange County Water Authority and other water authorities, as you know, Bill and David. And so I think I'll be in good shape if I just rely on him to make those connections. But I'm happy to talk to anybody about this.
Great. Kind of related question. One of the things that's implicit in your presentation is the need to, I suppose, build confidence within
Right.
people in the water sector that this is a set of technologies and the science behind it that could be extraordinarily efficient and useful and efficacious in a number of ways. You sort of implied this in terms of you mentioned the conservatism of agencies. What do you think it might take looking down the road to build confidence and trust in the water sector that this is something worth to invest in and worth partnering with UCI and others?
Yeah, I think two things. One is we need good demonstration projects like the one in Rialto to just show people, look, it's hard to argue with that. Um, if they'll believe we did the test, appropriately and everything, but you never know. There's skeptics everywhere. But I think the other problem is communication. It's getting the message to enough people uh, who can make decisions that are going to make this go. And what I found is it's really hard to get your message out there to a large number of people. And I think one of the problems is, first of all, I'm not a water guy, and I don't naturally go to the kinds of meetings that I probably should be going to talk about this. And so a lot of people haven't heard my message. And I still find publications out there coming out on other theories of nanobubble stability that aren't as good as ours, and they don't reference our work. So our paper's out there, but not everybody's reading it, of course. And I don't know, there's so many distractions on the internet, things coming at us from all different directions now. We can't rely on a publication, even in a good journal like we published in, to make a huge impact because, not many people are going to read it, unfortunately. And so I need to go to more conferences. And I've given Diego some slides. Hopefully and I know he'll use them. But we need to get the message out that, look, this has got some really good evidence for what it's doing, and it's worth trying. It's worth doing some exploration to see if this will work for your particular situation. So
Great
Uh,
point.
so that's I think that those are the two problems, you know. I'm not in the right groups all the time to be giving this message out, and so I don't do that naturally. And the other problem is just even if you are in those groups, to make it a concerted, impactful message that reaches a lot of people, it's not as easy as it used to be, seems like.
No, it isn't. And in Water UCI, we certainly understand that. We've had the good fortune of being able to work with a number of agencies on topics comparable to this. Along those lines, Bill had another great suggestion that Orange County Water District has a great R&D group. Maybe if you gave a talk to them, you could extend the RO, and I think they'd be interested. And we do have some connections down the road. Jim, if you're interested, we'll put you in touch with some of the great folks at OCWD. Occurs to me also, building on Bill's comment, the Metropolitan Water District, Southern California, I would think might be interested in this, particularly as they move forward with greater robustness on recycled and reused wastewater. And then I just want to make a quick announcement. Uh, this talk is being recorded, and in a few days, we will have a link posted to the Water UCI website for those that want to revisit it or haven't had the opportunity. And please share with your friends and colleagues about this talk. Yeah, again, great job. We're just
Well,
about
thank you,
up.
David.
Oh, thank you. Thank you, Jim. This was wonderful
Well,
and
like I
just a
said, yeah.
fascinating topic.
Well, this is the kind of webinar I need to be on, and I'm going to be trying to do more of them in the future. And I think with your help and Diego's help, we will get the word out. Maybe Bill will be able to help too. I don't know. He can
I
stop
think Bill would be
catching
well
butterflies.
equipped to help.
Yeah.
Absolutely.
All right.
Yeah,
Thanks everybody for
we'll do
coming
our
on.
best.
Yeah.
Thank you, everybody. Great. And thank you, UCI, Water UCI staff, Jungduck and Kayla, for all of your work, and Han Parker with the School of Social Ecology, which is where our center is headquartered. Uh, Stay tuned. We will have additional colloquia coming up later this year, and we'll send out a couple of email blasts on that soon. So again, Jim Earthman, wonderful talk. Thank you.
Thank you.
Take care, everyone.